All right. So this week I'm going to be talking about a paper called Deep Extreme Cut from Extreme Points to Object Segmentation. Um, the basically the point of the paper is to solve the problem of doing semantic segmentation or object segmentation or instance segmentation from in a more efficient way. So normally to do segmentation, you need a pixel map, and to annotate things like pixel by pixel um, by hand is actually very difficult. You have to draw in each little point. So going back to this one, you can see for the person, you kind of have to go around where the handlebars are over here, going down to their feet and kind of where their hand is around the handlebar. All this is kind of a bit it's a bit cumbersome. And for in the picture to the right with the car, you basically have to annotate not only the car, but you also have to kind of remove where the person is. Um, and especially like in between his legs and stuff. So this basically means that the fully supervised method, while the best performing, is pretty cumbersome to use. Um, so what people thought of doing is kind of have weakly supervised methods. So, I mean, there are, I guess, like totally unsupervised methods. Something that we've been actually trying with these these kind of using the heat maps from our classification networks. But weakly supervised methods are generally things where you kind of tell you basically take an object segmentation or like a bounding box, and then, or some other sort of object, and then try to, from that like less, that kind of less exact label to go to the semantic segmentation. Generally, the results are significantly worse than fully supervised methods. They are easier to obtain than full segmentation maps, but they're actually like not super easy. Like even having bounding boxes is kind of a bit, it's a bit cumbersome. And so kind of one of the points the authors makes about bounding boxes, or they take from someone else's paper about bounding boxes, is that to kind of create a bounding box, if you think about it, let's say our object is not perfectly square. In this case, I've got a cloud. So to like create a bounding box, you kind of have to go like somewhere outside of your cloud or somewhere outside of your object that you know kind of still encompasses your object, but is also like kind of close to the edges of the object. And so that would be like the top left corner. And it's not really like super intuitive, like where that point is. Normally people just make, do that. They drag it over to the other side and then kind of see where that side ends up, and then kind of drag it over again back to the other side to kind of fix the original point. But it's actually pretty cumbersome. It's not, it's definitely much better than like drawing the outline and filling in the whole cloud, but it's not super quick. So someone found that you can actually get the bounding box by just clicking on the four most extreme points of any object that you're trying to annotate. So in this case, you take the topmost point, the leftmost point, the rightmost point, and the bottommost point. And from that, you basically have this, not only the same information as the bounding box, because you now know, I mean, you can easily create a box from this if you think about just kind of connecting the points with lines. But also you have points that are actually, a point of this new kind of bounding box that's actually on the object itself. And so that information can be used to in a classifier of some sort. So here, yes, is kind of what extreme points are. It's also easier and more intuitive to create an extreme point because you're kind of clicking the object yourself. You're not really clicking somewhere to the outside of the object or kind of dragging things. And although the extreme points I say are 4 points here, you can actually add more points if you really need them. The authors later on kind of use extreme points as something that you can use as a refining tool. So if your 4 extreme points kind of don't create the segmentation mask you want it to, you could actually add like 5 or 6 or more points on the object to create the box that you want, or create the mask that you want. Okay. So some related works, the fully supervised segmentation methods. So there's kind of the deep lab work, which I believe is the atrocious, the ASSP networks. And then there are also the pyramid scene parsing networks. Kind of the difference between those two is that the pyramid scene parsing networks kind of take in global information, whereas the deep lab work really only uses the convolutional level information. There are also image level labels. So, we've been using GradCam here. People probably heard of that. Other weakly supervised methods are something called scribble labels. So a scribble label is basically you kind of quickly draw a line. It doesn't have to be a straight line. It could just be like if you just imagine taking a pen and like slashing over what the object is, that is kind of what a scribble label is. So you kind of would just make little tick marks all over your image for different objects. And every tick mark or every mark would kind of be an object. Other methods, an older method is called like grab cut. You can actually use this in the OpenCV library. It is also basically takes a bounding box and turns it into a segmentation mask, and it's kind of an older algorithm. It's not deep learning based, but it works if your object kind of has the same colors or kind of contrasting colors from the background. But if your object kind of looks like the background, then it doesn't work that well in general. All right, so let's see what they did in the paper. So basically what they're doing in the paper is the extreme, so the way they get the segmentation mask is they get the input from either a user, or sometimes they'll create like fake input, basically they'll take a noisy version of the actual mask and then use that as input. But the input is these 4 points. You click 4 points on the image, and then it does a kind of Gaussian blur of these points, because obviously you've just chosen a single pixel. But the idea is that perhaps your single pixel is not super exact. So they kind of create these Gaussian blurred points. It's actually kind of looks a lot like this. It looks like these red points here. So kind of you would pick something like right in the middle of that red point, and it would blur that into what the red point is. Sorry. And so that is a heat map just with 4 heat points on it. It uses that as an input to a CNN. It also crops the image based on that input. This crop is not super tight. They have a padding on the crop because again, it wants some background information or some background to the image, not just all foreground. And it's possible that perhaps the extreme points were not perfectly created. Here's a visualization of the process. So you have a picture of the guy, and I basically tried to pick 4 points. You can see these 4 points on the image on the right, those little green X's. So there's one like on top of his hat. There's kind of one at the guy's right elbow that's at the left side of the screen. There's one at his left elbow, which is on the right side of the screen. And then there's kind of one down below near the napkin. So you select those 4 points, and then it creates this kind of Gaussian blurred mask, which is that second image with those 4 points. And then the network will create a segmentation mask of what it thinks is most likely the object, in this case, the person. All right. So the architecture is a ResNet 101 base. They've removed the fully connected layers and the max pooling layers, and they switched those out with either the atrocious convolution with the PSP module head or the less sophisticated, the ASSP, which I'm forgetting the acronym, but it's another atrocious convolution or dialogue convolution. So this is kind of just it does a classic Gnostic output. So since you're only inputting one mask at a time, it's only basically doing a foreground background check. It's not checking between several classes. It really just does one. And it uses a weighted cross entropy loss. They also tried different losses such as the BCD loss, but found that this one works the best. So here are some results. So on the right side is kind of a study they used based on basically using different techniques. So you can see which techniques increased or decreased their like gain and intersection over union. So kind of using the region-based, the top line region-based is sort of a like mask RCNN style region proposals, or kind of a deep lab style scene parsing network, parsing scene network as a base. And they found that the deep lab worked better. Then they kind of compared bounding boxes to extreme points. And you can see that the extreme points do better. The balanced BCE, I sort of feel as though that might be a typo because they do talk about the balanced cross entropy. But anyways, that's basically just using the inverse. They use the inverse of the frequency of the class to weight the cross entropy loss. The biggest gain they get is from the cropping the image. So basically cropping the image based on the extreme points, which makes a lot of sense because you're kind of getting rid of a lot of the background images and the network no longer needs to actually consider those things. And I think that's kind of like a big, and that's not, I wouldn't say one of the flaws, but one of the things that I kind of thought of is like, well, if you're just using the cropping and you have like an actual person kind of clicking these points for you, it seems pretty obvious that you're going to have a much easier time identifying the object if you kind of already know the object is basically centered within your picture. And so, yeah, but it makes a big difference. So, and then here they've got the PSP. On the left, you kind of see their network versus a bunch of different other types of semi-supervised methods. So I won't really go into all of those, but you can see that their method does work the best relative to all the other semi-supervised methods. And again, you can see that their method also kind of works better than the Deep Lab, like kind of the original Deep Lab V2. I also did look at kind of the newer Deep Lab. I think it's Deep Lab V3. And those numbers, it's a little hard to compare because they're not using the same validation set, but those numbers were slightly better than these numbers, just for comparison. All right. One thing they also kind of make a big point of is that it actually takes like less time. I kind of mentioned this before, but like creating bounding box is kind of cumbersome. They also find that all these other semi-supervised methods where you kind of have a user like making clicks around the point or around the object, they also are quite cumbersome. So I guess a lot of these other methods, basically they kind of, you click around the object and it sort of iteratively like figures out where the object kind of is. It gets better and better and better. And so this is why it can take more than, it can take basically 7.5 clicks for like IFCN. It's not just a set number of clicks. This one, yeah, it basically works with 4 clicks. They do mention that you can add more clicks, but they don't really, I didn't really see too much information about how much that increases or decreases the error rates. And on the right, you can also see basically their method versus a bunch of different versions of GraphCut, which again is super popular. All right, so kind of the highlights of it are there's an 11% or 12%, almost 12% increase over the Deep Lab V2 on Pascal dataset. The time savings is an order of magnitude higher versus traditional segmentation tasks. Quickly going back, those are these graphs at the bottom. So these graphs are kind of the x-axis is the budgeted hours on a logarithmic graph, budget of annotation hours. And so you can see that there you kind of get a maximum, or you get to like 70% and medium intersection over union at maybe 3 hours. Well, it takes almost 70 hours to do the same thing with the other methods. And also on the previous slide there, you can see that there are less clicks involved. It was like 4 relative to like almost 20 or over 20 for some of the other ones. So here are some of the possible pitfalls that kind of I saw reading the paper. So a large portion of the increase comes from just cropping the image. And I mean, that method is going to work well with, I think, any method. I know GraphCut is kind of one of the things that, one of the ways it works. This network structure really only allows for a single object per pass. So if you want a user to like annotate like 5 different objects, let's say, you have to like get the 4 extreme points for one object, put that through the network, then get 4 new extreme points for another object, put that through the network, and then 4 more. Because the way it kind of works is it has that one, it basically adds a layer or it adds a channel to the image. So like, the input to the CNN is a 4 channel image, one channel being that heat map. And so you can't have like you can't stack like multiple heat maps and run them all at once. You kind of always need that 4th channel to be a set of a set of extreme points. And the network's going to assume that those extreme points always relate to just one object. So another pitfall is, I mean, it's kind of a pitfall, but it says that it still requires human input. And so, I mean, everything kind of requires human input, but it is far less than a segmentation mask. And the other problem is that the model doesn't necessarily generalize to different classes, given, if you're training on the Pascal VOC set, it's going to work really well at like looking at people. But if you kind of have it look at something else, it's not super great. All right, and so here are the results. It's pretty impressive, and it's really easy to use. So they have the implementation that I'm going to try to show you right now, and it's pretty dead simple to use. And so if you kind of want to insert this into like a Mechanical Turk style product that you are using to get people to annotate things, it would be great. But yeah, I'm not sure how well it generalizes. All right, and I'll post this to the chat, to the Slack, so you can get all the references and check it out yourself. And now I'm going to take a look at the implementation they had. So all right, so here's the demo that you kind of saw before. I will choose really quickly like the one that I chose before. So in this case, you can see that, or can you guys see this? I'm just assuming you can see my screen.
We're seeing the presentation still. I don't know if that's what everyone.
Okay. Okay. Let me.
Not the whole presentation, but like we see your browser and we see the 3 tabs at the top, but it's still on the. Oh, yeah. Very good.
Now something new. Okay. Sweet. All right. Well, I'm gonna. Let's see what I'm sharing now. I think I'm sharing my desktop. So, all right. All right. So, I'm gonna click the same thing I did before. And you'll see it'll get the person because it's actually been trained to find people. Kind of works really well. But if you have it do something that it's not pre-trained on, let's say like an omelet, and like to me it seems pretty obvious like where this omelet is, right? And it does an okay job, but you can see it kind of like misses the edges. I mean, this seems like it should be the omelet. That seems like it should be the omelet. I mean, for one, it's not quite as good as the person. Um, and yeah, I mean, I guess that's kind of a demonstration of it. And you can also see that, I mean, it is dead easy to like use this. Um, and it's relatively fast. I mean, this is just on my laptop. And it's a pretty unoptimized version, but you can get the results pretty quick. All right. Is there any questions?
No, good stuff, David.
All right. Well, if there are no questions, I'll let you guys go.